All right, let's talk about 6.4, the length of a plane curve. Now remember, the topic of discussion in this chapter, chapter 6, is about some applications of integration. And so far, all we've done is talked about a bunch of mathy stuff. So we haven't really seen much application to the real world, I guess. But we will see some applications to the real world starting, I believe, in the next section. So in the next one, I think, well, in 6.6, we talk about work. In 6.5, no, 6.5, we're still talking about mathy stuff. Anyway, so we have a couple more. So this section and then the next one is some more mathy stuff. But then we'll start to talk about applications in the real world. Personally, I prefer the mathy stuff. But, you know, that's just me. Anyway, so in 6.1, we talked about the area between two curves. And then in 6.2 and 6.3, we talked about the volume of solids of rotation. So 6.2 is about disk washer method. 6.3 was about cylindrical shells method. Another thing that we can do with integration is we can calculate the length of a curve. So here's how that works. So if f of x is differentiable, and if f prime is continuous. Now, the reason we require f prime to be continuous and f to be differentiable is so that f is a smooth curve. So this is just a mathy way of saying that if f is a smooth curve, right? So if f is a smooth curve on the interval from a to b, then the arc length L of this curve on AB is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. So kind of a weird formula. You might wonder, well, where in the world does that come from? Well, let's talk about it. So first of all, if we want to find the arc length, one thing that we could do is we could approximate it, right? So we can approximate the arc length by breaking the curve into smaller and smaller line segments. So obviously, if you only use the endpoints, you're going to get this straight line. That's not a very good approximation. But if you use these 3 points, you get these 2 line segments, and if you add their lengths together, you get a better approximation for the length of the curve. And, you know, if you use 1, 2, 3, 4, 5 points instead of just 3, then you get an even better approximation. And if you use a whole bunch of points, then you get an even better approximation. How many points? I think 9 maybe. But yeah, so the more line segments we break this down into, the better our approximation is going to be. And based on your knowledge of calculus, you can probably see where that's heading, right? So that if we broke this down into an infinite number of line segments, then we don't get an approximation anymore. We get the exact value. We get the exact value of the arc length. So let's see if we can come up with a formula for that, right? So we can call these points, we can insert points x1, x2, and so forth, all the way to x minus 1 between a and b. And a we'll call x0, so it's our very starting point, and b we'll call xn, so it's our end point, right? So if we're thinking this is a and this is b, then we insert a bunch of points in between, right, that we're calling x1, x2, x3, and so forth. Now, let's think about the length of the kth line segment. So if we just chose an arbitrary one like this one, right? What is its length? How would we figure out the length there? Well, let me use my pencil. So how would we figure out the length of this line segment? Well, we called this point x1, x2, and we called this point x3, and note that this is line segment 1, 2, 3. So this is the third. So for the third segment, okay, so in general, the length of the kth segment is going to be the distance between x sub k minus 1 and x sub k, right? So now x sub k minus 1, that's just the x coordinate. The y coordinate, of course, would be f of x sub k minus 1. And same thing for x sub k and f of x sub k. So we want to find, so the length of the kth line segment is just the distance between those 2 points. So we can use the distance formula, right? So we use distance formula, and note that xk minus xk minus 1, we can just call that delta x. Okay. Now, oh, sorry. This you can see better, right? xk minus 1 is delta x. Now, here's where we use some old results from our Calculus 1 class, like the mean value theorem. By the mean value theorem, we know that there's a point, which we'll call xk star, and this point is between xk minus 1 and xk. So we know that there exists this point xk star such that the derivative of f at xk star is the same thing as the average rate of change, or in other words, the slope between the points xk minus 1 and xk. Well, so if we solve this for xk, f of xk minus f of xk minus 1, right, this little bit right here, if we solve this expression or this equation for this numerator, then we see that f of xk minus f of xk minus 1 is f prime of xk star times delta x, right? Because xk minus 1 is just delta x. Okay, now we make that replacement. So the length of the kth line segment, remember, is the square root of delta x squared plus f of xk minus f of xk minus 1 squared. Now we replace this with this expression, right? And we still have to square it. So we get f prime of xk star squared times delta x squared. We can factor out a delta x squared and then take the square root of delta x squared to just get delta x, and we can pull that out of the square root, and then this is what we're left with, 1 plus f prime of xk star squared. This is starting to look a lot like this, which is the result that we were trying to prove at the beginning, right? So you can start to kind of see, where that formula comes from. Well, but this is just the length of the kth line segment. If we wanted to find the overall arc length, well, we would have to add up all k segments, or all n segments, right? All n segments. So an approximation for the entire arc length, L, is the sum of all of the LKs, right? So L is approximately the sum from k equals 1 to n of LK. In other words, it would be the sum from k equals 1 to n of this thing, right? 1 plus square root of 1 plus fk star squared times delta x. So to get the exact value for L, we take the limit as n goes to infinity, right? We take the limit as n goes to infinity of this thing, and that's just going to turn into the integral, of course. And there you go, we've proven it. So we've proven that this formula will work for calculating the length, the arc length of a curve. So it's pretty nice. I'm not going to take you through the proof of this, but obviously a similar statement could be made if we were to integrate with respect to y. So for a curve of the form g of y, the arc length from y equals c to y equals d would just be the integral from c to d of square root of 1 plus g prime of y squared dy. And so I'll show you an example of each formula, but we're actually going to do it for the same function. So it says, find the arc length of the curve y equals x to the 3 halves from 1, 1 to 2, 2 root 2. And we're going to do this by differentiating with respect to x, and then we'll do it again by differentiating with respect to y. We should get the same answer, obviously, both times. So let's see if we can do it. Okay, so the curve is y equals x to the 3 halves, and we want to calculate the length of the arc length from 1, 1 to 2, 2 root 2. Okay, so the length of the arc is going to be the integral from a to b, and in this case we're integrating with respect to x, so we use the x coordinates, right? So it's from 1 to 2 of the square root of 1 plus f prime of x dx. Oh, I'm sorry, and I have to square that. dx. Okay, so the first order of business, I think, is to find the derivative. I mean, we called this y, but you could call it f of x, right? So we need to find the derivative. We can say, well, y prime is going to be 3/2 x to the 1/2, right? So that's what we're going to plug in right there. So we're going to say L equals the integral from 1 to 2 of the square root of 1 plus y prime squared dx. So this would be the square root of 1 plus 9/4 x. Right? X to the 1/2 squared would just be x. Okay. I'm going to do a u substitution to make this a little easier. So let's let u equal 1 plus 9/4 x. Right? And then du would be 9/4 dx. So I can put a 9/4 here on the dx, as long as I offset it with a 4/9 out there. And then this thing will become du. And this thing will just become u. So what we're going to end up with at the end of the day, oh, maybe we should change our limits of integration too, right? So if x equals 1, u equals 1 plus 9/4, so that would be 4/4 plus 9/4, so 13/4. And when x equals 2, u would be 2 times 9/4 is 18/4, or 9/2, in other words. So 9/2 plus 1 would be 9/2 plus 2/2, so that's 11/2. Okay, so now we can make the replacements. So we can say L equals the integral from, now we're doing everything in terms of u, so it's going to be the integral from 13/4 to 11/2, the integral of the square root of u du. Oh, that's easy. That was much easier than I was expecting. Alright, this is just u to the 1/2 power. So the integral is going to be u to the 3/2 divided by 3/2, or in other words, 2/3 times u to the 3/2. So this is 2/3 u to the 3/2 evaluated from 13/4 to 11/2. By the way, if you don't like changing your limits of integration, then what you could do is, instead of changing the limits, just evaluate the indefinite integral, and then at this step, back substitute. So plug in 1 plus 9/4 x for u, and then you can just plug in your original limits of integration, 1 and 2. So you would get the same answers that way. This is not going to be nice. Holy schmoly. Because we have to take 11/2 to the 3/2 power. Oh, goodness. So it's going to be 2/3 times, we'll say 11/2 to the 3/2 power minus 13/4 to the 3/2 power. And I have a feeling that that's probably as nice as that's going to ever look. You know what I mean? You're not going to get a nice looking answer here. I wonder what this is approximately. So I'm going to plug this into my calculator. 2/3 times 11/2 to the 3/2 minus 13/4 to the 3/2. Actually, so because my calculator is so nice, it will actually give me the exact value, arranged slightly different. So it's saying the exact value would be negative 13 root 13 plus 22 root 22 divided by 12. So like if you went through the trouble of like rationalizing and everything, that's what you would get at the end of the day. Kind of interesting. But what's the approximate value? So this is approximately hold on. Okay, sorry, I'm checking my answers as I go in the book, and I've come up with the wrong answer, but I know why. The reason is because I forgot the 4/9. Some of you were probably like yelling that at me this whole time, right? So I need to have another 4/9 out here, which means, oh goodness, this is wrong. This is wrong. I'm not gonna, well, let me go back. So I'm gonna say 4/9 times all of this junk. Okay, so what you should actually get is negative 13 root 13 plus 22 root 22 over 27, which is approximately 2.09, and that does agree with what the book got. So okay, so I'm sorry, I forgot this 4/9, silly me. Yeah, forgot the 4/9, but that's the correct answer. Okay, very good. So there's the arc length. Let's do another one. Oh well, the same one, right? The same one, just integrating with respect to y. So again, we've got y equals, what was it now? X to the 3/2 from 1 to 2 root 2. Okay, now if we're gonna integrate with respect to y, then we need to solve this for x. So that means that I'm going to have to raise both sides. If I want to get just x by itself, I need to raise both sides to the 2/3 power, right? So I get x equals y to the 2/3. I also need to differentiate, right? So I can say, what is dx? I need to integrate with respect to y, right? So usually we're so used to writing dy dx, but I'm integrating with respect to y, so I want to do dx dy. Okay, so integrating with respect to y, I'm going to get 2/3 y to the negative 1/3. Okay. So I think I'm ready to plug stuff into my formula. So the formula I'm going to use this time is for when you're integrating with respect to y. It's the same thing, right? Same formula. It's just you're integrating with respect to y. So this is going to be integral from. Now I have to use the y coordinates because I'm integrating with respect to y. So I'm going to go from 1 to 2 root 2. And I'm going to do square root of 1 plus dx dy squared dy. Okay, so there's the setup. The rest is history. Right? The rest is just calculus. Easy squeezy. Let's see if we can finish it. So 1 to 2 root 2 square root. This is going to be, well, 1 plus 4/9 y to the negative 2/3. Okay. How in the world do I integrate that? if I do a u substitution, I'm just going to make things worse, right? If I do a u substitution, I'm going to get du equals negative 8/27 y to the negative 5/3, which is not nice at all. Maybe I can play with this algebraically a little bit. As you can see, these things are not, generally speaking, easy to integrate. But that's all right. Okay. You know what? Actually, what if I factor out a y to the negative 2/3? Yeah. Okay. So forget this step. I'm going to factor out a y to the negative 2/3. Because I can take the square root of that and remove it outside of the radical, and that gives me some hope that when I do some u substitution, I'll have what I need sitting outside the radical. So I think this is the thing to do. So if I factor out a y to the negative 2/3, then I'd have to divide. 1 divided by y to the negative 2/3 is just y to the positive 2/3. And here I would have, well, whatever. I was going to try to take the square root of that. It's fine. Here I would just have a 4/9 left over, so plus 4/9. Why not? So I'm going to go one step further. 2√2. I can take the y to the negative 2/3 out of the radical now. So I can call this square root of y to the 2/3 plus 4/9 times, if I take the square root of y to the negative 2/3, I get y to the negative 1/3 dy. Perfect, right? Yes. Oh, I love it when a plan comes together. So look, now if I let u be y to the 2/3 plus 4/9, I'm going to get du equals 2/3 y to the negative 1/3 dy. There it is. Okay, cool. Cool. So let u equal y to the 2/3 plus 4/9. Then du equals 2/3 y to the negative 1/3 dy. So all I have to do to fix this thing up is put a 2/3 there, which I'm allowed to do as long as I offset it with a 3/2 there. And now this whole thing, 2/3 y to the negative 1/3 dy, this is du. This whole thing is u. And I'll try not to forget to bring along my coefficient this time. All right. We should change our limits of integration. I'm not looking forward to that. But let's see. So at x equals 1, or sorry, this is at y equals 1. So at y equals 1, u equals 1 to the 2/3 is just 1. 1 plus 4/9 is 13/9. Oh, that's not bad. And at y equals 2√2, this might not be so nice. U equals 2√2. We have to take the cube root of that and then square it. Or we could square it first and then take the cube root. I'd rather do that. So Let's square it first. 2 root 2 squared, that's going to be 4 times 2, which is 8. Oh, and the cube root of 8 is 2. That's actually really nice. Ooh, that one ended up okay. All right. Let's do this then. So we have, so we're going to have 3 halves times the integral from 13/9 to 2 of square root of u du, and that's all there is to it. So this is 3 halves times, this is going to be x to the 3 halves divided by 3 halves. So x to the 3 halves times 2/3. Or u to the 3 halves times 2/3. How did this end up so nice? I almost feel like I've done something wrong because this is ending up so nice. U to the 3 halves, do you ever have that feeling? 13/9 to 2. Oh, but now it gets ugly, doesn't it? So you plug in the 2 and what do you get? You get 2 cubed is 8, then you take the square root, you get 2 root 2, right? So you get 2 root 2 minus, I don't even want to think, 13/9 to the 3 halves power. I mean, square root of 9 is 3, and then cubed is 27, so you get a 27 down there. But the 13 isn't nice at all. So I wonder what my handy-dandy calculator will give us here. 2 root 2 minus 13/9 to the 3 halves power. It's just giving us, it's giving me 2 root 2 minus 13 root 13 over 27. Shoot. Somehow I'm getting I'm getting the wrong answer. I'm getting 1.09. Where did I go wrong? Because we should be getting 2.09, right? Approximately 2.09. What did I do? What did I do this time? I needed for there to be a 2/3. I put a 3 halves, so 3 halves, 3 halves. 3 halves times 2/3 does cancel, right? So it's u to the 1/2 goes to u to the 3 halves divided by 3 halves, which is times 2/3. Those cancel. What went wrong here? U to the y to the 2/3 plus 4/9. Y to the negative 1/3. That looks good. Was it my limits of integration? Maybe it was the limits of integration. At u equals, or at y equals 1, at y equals 1, u would be 1 plus 4/9. That's 9/9, so that's 13/9. That's okay. At y equals 2 root 2, maybe this is what it was. Ah, yeah, I forgot to add the 4/9. Gosh, dang it. So 2 root 2 to the 2/3. Well, 2 root 2 squared, as we said, was 8, and cube root of 8 is 2. So it's 2, but it's 2 plus a 4/9. Gosh. Okay, so 2 is 18/9. 18/9 plus 4 is 22/9. That should have been 22/9. I knew something was fishy. It was looking too good. Okay, so this is going to be 22/9 to the 3 halves minus 13/9 to the 3 halves. Okay, 22/9 to the 3 halves minus 13/9 to the 3 halves. Is equal to 22 root 22 over 27 minus 13 root 13 over 27, and it's approximately 2.09. Okay, well, there you go. Goodness gracious. So 2 arithmetic mistakes out of 2 problems. What are you going to do with me? Oh well, at least I caught them, right? And that's it. That's all I want to say about the arc length, or the length of a plane curve.